Hi everyone! In the previous video, we have proved the quadratic convergence of the Newton algorithm under some standard assumptions, which are the regularity, the simplicity, and the vicinity. Starting from this section, we will take a closer look at the performance of the Newton iteration when each of these conditions fails. Let us begin by assuming that the regularity condition is violated, in the sense that the function under consideration is no longer of class C2. Now, depending on how badly things are breaking down, we might want to distinguish between two scenarios. In the first scenario, even the convergence is not available anymore. The sequence under the Newton iteration will diverge. While in the second scenario, although the convergence is still there, it will no longer be a quadratic one, so that the convergence is fairly slow. It might be useful if we can have a criteria that helps us determine which scenario we're in. To this end, let us look at the following theorem. And you can see the assumptions here are pretty much similar to the assumptions in the theorem of quadratic convergence of Newton's method we discussed in the previous section, except that here we have weakened the regularity assumption from class C2 to class C1. In other words, we still know that f and f prime are continuous functions, but there's nothing we can say about the second derivative of f. We don't even know if it exists or not to mention its continuity. Under these assumptions, we show that the function under consideration will still converge, even superlinearly. The proof of this theorem also relies on Taylor theorem. To this end, let us apply the Taylor theorem to fx centered at x star. That gives fx is equal to fx star, which is equal to 0, plus f prime x star times x minus x star, plus a function hx times x minus x star, where the limit of h as x approaches x star will be 0. You can see there is a key difference between the Taylor theorem here and the Taylor theorem in the previous section. As now we no longer have C2 regularity, we don't have the Lagrange remainder anymore. However, since the function is still C1, we can still use the Peano remainder. And this key difference will essentially impact our estimate for the rate of convergence later on. Now, before we go any further, let us first prepare some basic estimates. Let us denote by C the absolute value of f prime x star. Since x star is a simple root, we know that this value is strictly greater than 0. Now, recall that f prime is a continuous function, and the limit of hx is going to be 0 when x goes to x star. Thus, we can choose a positive real number delta, which might be fairly small, such that for any x in the delta neighborhood of x star, the following three conditions will be satisfied at the same time. First, the absolute value of f prime x will be greater than or equal to c over 2. This is due to the local sign definiteness for a continuous function. Second, the absolute value of fx minus fx star will be less than or equal to c over 8. This is again due to the continuity of f prime. Last but not least, the absolute value of hx will be less than or equal to c over 8 as well. This is because the limit of h when x goes to x star is equal to 0. Thus, when x is fairly close to x star, we can make sure this quantity is as small as we want. Putting all the three pieces above together, we see that when the distance between x and x star is less than or equal to delta, the quantity absolute value of f prime x minus f prime x star plus the absolute value of hx divided by the absolute value of f prime x is bounded from above by c over 8 plus c over 8 divided by c over 2, which turns out to be 1 over 2. Now with this estimate in our pocket, let us proceed to the Newton iteration. As usual, xn plus 1 minus x star is equal to xn minus fxn over f prime xn minus x star. Now moving the items on the numerator, it becomes f prime xn times xn minus x star minus fxn. Now replace fxn by the Taylor formula with the Peano remainder. We see that the whole term becomes f prime xn minus f prime x star, then minus hx divided by f prime xn, altogether multiplying xn minus x star. Now, if the distance between xn and x star is indeed less than or equal to delta, upon taking absolute value, we see that the absolute value of xn plus 1 minus x star is less than or equal to the absolute value of f prime xn minus f prime x star plus the absolute value of hx divided by the absolute value of f prime xn, altogether multiplying the absolute value of xn minus x star. Here, notice that we have applied the triangle inequality for the numerator. Now, since xn is in the delta neighborhood of x star, the estimate we have achieved previously is valid here, so this whole quotient is less than or equal to 1/2. This is actually the same line as we have seen in the proof of quadratic convergence in the previous section. So similarly as in the previous section, we conclude that if our initial value x0 is already in this delta neighborhood of x star, then the sequence under the Newton iteration will converge to x star. We can even go one step further to estimate the rate of convergence here. Actually, by dividing xn minus x star on both hand side and taking the absolute value, we see that the limit of the left-hand side is equal to the limit of the right-hand side. But now, since we already know that xn is converging to x star, this shows that the Newton iteration will converge superlinearly. This is clearly better than nothing, although it is in general not as fast as a quadratic convergence. In other words, if your function is at least C1, then you don't need to worry about the convergence. It will converge. The matter is how fast it is going to converge. On the other hand, if your function is not even C1, then perhaps you should be prepared for some worse scenarios under the Newton iteration, that the sequence might not even converge. We will illustrate such subtle differences by examples in the next section.